let's say dx dt equals negative 2x minus 2y, and dy dt equals negative x minus 3y. Without doing any in-depth linear algebra calculations, we can get an idea for what the phase plane of this system looks like just by thinking about nullclines, which is why I introduced nullclines early. If we set both right-hand side functions equal to 0, the resulting equations define lines in the plane that are nullclines of the system. Lines where, for the vector field, the arrows are either vertical or horizontal. And that helps you draw the phase plane. So the x nullcline is where dx dt equals 0. The vector field is going to be vertical. The vectors in the vector field are going to have 0 first component. They'll be either pointing straight up or straight down. Or in the special case of the origin, they will just be a big dot. Again, that's negative 2x minus 2y equals 0. You can solve that for y as a function of x by adding 2y to both sides and then dividing by 2 to get y equals negative x. The line to the origin with a slope of negative 1 is the x nullcline. The y nullcline is where dy dt equals 0. This is really where I'm using the fact that I'm setting these things equal to 0. So that's where negative x minus 3y equals 0. And solving for y as a function of x, that will mean y is negative 1/3 x. If you add 3y to both sides and then divide both sides by 3. So now we have two lines in the plane. Here's our xy plane. Make it kind of big. X there, y there. One of which has a slope of negative 1 and one which has a slope of negative 1/3. Let me make them in different colors. So this is going to be the line to the origin with a slope of negative 1. That's the x nullcline. That's along with that, dx dt is 0. So I make a bunch of little vertical lines crossing that nullcline, that x nullcline, indicating to myself that solutions have to cross that vertically with a vertical velocity vector. And the y nullcline goes to the origin and has a slope of negative 1/3, like this. Solutions have to cross that horizontally with 0 second component. Where x and y nullclines intersect, you have equilibrium points. That's only one point, the origin. If you think about solving this system of equations here, the system of homogeneous linear equations, the determinant of the corresponding coefficient matrix would be non-zero. There's only a unique solution, just the origin. The kernel of the corresponding linear transformation would be just the origin. You can relate this a little bit to linear algebra in that way. Somebody mind catching that door? Alan, do you mind doing that? Thanks. But how do I decide what the other solutions look like? These two lines, these two nullclines, split the plane into 4 regions. This region up here, this region over here, this region over here, and this region over here, over which the vector field points either northeast, northwest, southeast, or southwest. How do you tell? Well, you can just plug in some points. For example, if you imagine taking a point in the first quadrant here where x and y are both positive, and plugging those coordinates into these right-hand side functions, you're going to get negative quantities, right? Because of all those negative signs. In other words, dx dt and dy dt are both negative. X and y are both decreasing functions of t. Solutions have to go to the southwest. as time increases, because that's the direction where x and y both decrease. On the flip side, if you're down here, when in the third quadrant where x and y are both negative, then when you plug them in up here, you get positive quantities. dx dt and dy dt are both positive. Solutions must increase. X and y must increase over time. So solutions go to the northeast. In this wedge over here, x is negative and y is positive. What's an example of a point over here? Well, like this point here maybe would be the point. I don't know. Let me see. This is the line y equals negative x. X is -5, y is -4 probably would be an example of a point. Yeah, that would work. -5, -4. If you imagine plugging that point into the right-hand side, so x equals -5 and y equals -4. +4, thank you. X equals -5 and y equals +4. dx dt is 10 minus 8 is 2 is positive. And dy dt, the right-hand side, is negative of -5 minus 3 times 4 is 5 minus 12 is negative. dx dt is positive, so solutions move to the right. dy dt is negative, so solutions move down. To the right and down, they've got to go to the southeast. Over here, you'd find the flip. If x is +4 and y is -4, for example, those signs would change. Solutions go to the northwest. From just this much information, you can typically draw a decent phase plane here. Think about different initial conditions. For example, if you started right there, the solution has to move to the northeast because you're in this region below the red and green lines here. So it's got to head up this way. It's going to cross this x nullcline with a vertical tangent. Will it cross the y nullcline? No, because it's now going to the northwest. There's no way it's going to cross that red line with a horizontal tangent. So it's forced now to head toward the origin. If, on the other hand, I start over here far enough, and I'm going to the northeast, I cross the red y nullcline with a horizontal tangent, and there's no way I'm going to cross that green line with a vertical tangent, because I have to go to the southeast. If I cross that one like that, I wouldn't be going to the southeast anymore. If I start over here, this point ends up being kind of the mirror of this point. I got to go to the southwest, cross horizontally, and then head to the northwest. Or these solutions are going to the origin. The origin seems to be some sort of sink. Start over here. The solution has to head down this way. Can these solutions touch each other? They actually can't. We're going to see why soon in the lectures. I'm going to talk about uniqueness. Distinct solution curves can't touch each other. They can get really, really close together. They can get squeezed really, really close together, like in here and here, but they can't literally touch each other. I hope it seems reasonable that maybe over here there's a solution that heads straight toward the origin. That's supposed to be a straight line there. And over here, there's a solution that heads straight toward the origin. I hope that seems somewhat reasonable that that might be the case. It's called a straight line solution, and it will exist. And over here, there's also going to be a straight line solution that heads straight toward the origin, about like this and about like that. All other solutions, besides those straight lines and besides the origin, that's an equilibrium point, are curved, in spite of the fact that the system is linear. And yes, the origin is an equilibrium point that is a sink. Remember me making a big deal about change of coordinates, skew coordinates at the beginning of the lectures? these straight line solutions form a skew coordinate system for which the system can be transformed into its most simple form. I'll say that again. These straight line solutions that you see here that are not the axes, they're not the X and Y axes, they are skewed axes, so to speak. This is a big picture thing here. Form axes for a new coordinate system. Maybe you call it a U and a V coordinate system, under which this system can be transformed into its most simple form. It's a big, big deal. In fact, you might even say it's the biggest deal of the entire course, right there, what I just said. Okay. How do you do that? Essentially, these straight lines are parallel to a couple of vectors that will form a basis for the plane, the best basis to use, in fact. So now I'm connecting it to linear algebra. And the coordinate vectors, which if you've watched the lectures ahead of time enough, you've heard of before, 4 vectors in the plane with respect to that basis will be what we want to use to transform to the simpler system, to the simpler corresponding system. This is related to a simpler system using these new axes. Those vectors are called eigenvectors, and there are also numbers called eigenvalues related to this. Let me keep going with this example, and let's do some symbolic things, except we'll use technology, because we don't have the skill yet, the skills necessary to do it by hand yet. We will. Let me go ahead and enter this matrix, the coefficient matrix of the system, A. I'm looking at the coefficients of the right-hand side functions, -2, -2, -1, -3. Working right here. That's the coefficient matrix for the system of differential equations, of linear differential equations. In vector form, let's talk about vector form now. If I let vector capital Y have components little x, little y, so that its derivative, d capital Y dt, is a vector whose components are d little x dt and d little y dt. These things depend on time. This is going to be a function of time here. There's its derivative. It can be interpreted as a velocity vector for this ultimately parametric curve here. It's a function of t. I didn't put the t in there explicitly. And those curves, if they're going to be solutions of the system of differential equations, have to satisfy an equation where I have this, the coefficient matrix coming from those coefficients that you see here, what you see in Mathematica, times the vector y. -2, -2, -1, -3 times little x, little y. I could think of that as capital A times vector y. That is the vector form of the original system. In chapter 3 of the textbook, we're going to learn how to use eigenvalues and eigenvectors to solve this system, even by hand, without technology. For the moment, though, I'm going to use technology. There's a couple different ways I could use technology. One thing I could do is I could use d-solve value. It's been a while since I tried this, but I think I can use it in vector form like this. I think I could use curly braces, x prime of t, comma, y prime of t, and curly braces equals a times x of t, comma, y of t. The period means times. And I'm putting these things in lists that is a way Mathematica will treat them as vectors. I'm solving for both x of t and y of t, and t is the variable. I think this will work. I haven't tried it in vector form like this in a while, but let's see if this works. It did. It gave me an answer. And I could even look at the answer as a vector. This is a 2x1 vector. There's the first component. There's the second component. Kind of complicated, right? We're going to learn how to do that by hand. I could also solve a generic initial value problem by adding generic initial conditions in here. Let me put an extra set of curly braces around the differential equation. And then a comma. X of 0, comma, y of 0 equals x0, comma, y0. There's my generic initial condition right there. I know Mathematica syntax is kind of funny, but I think this is going to work. I thought it was going to work, maybe not. These solve value called with 2 arguments. Oh, you know what? I put it in the wrong place. I put this in the wrong place. That's why. There we go. So based on a generic initial condition, x equals x0, y equals y0, that's your solution. Do notice that it is exponential decay in all terms. As t goes to infinity, these terms are all going to 0. That's a symbolic reason why the origin is a sink here. All solutions head toward 0 as t goes to infinity. In the lectures, I've also talked about something called the matrix exponential and flows. That is related to this. So far, if you've kept up with the lectures, I've talked about flows in the context of scalar equations, scalar differential equations. I'm forgetting offhand what context I brought the matrix exponential up into. I'm about to summarize what you should have learned about that topic so far. Those 2 topics, actually, matrix exponential and flows. And then we'll have Mathematica confirm what I say. Okay? This is a big deal. For a generic initial value problem in vector form, dy dt equals a times y, and y of 0 equals y sub 0, y naught if you prefer, we can write down the unique solution very simply. I call this the beautiful generalization. What is it a beautiful generalization of? I will explain that in a minute. What I'm about to write applies in any dimension, in fact. Y in general could be an n by 1 vector. In other words, an element of Rn, where n is an arbitrary positive integer. A then would have to be an n by n matrix. Y sub 0 or y naught would also have to be an n-dimensional vector. Right, as a column vector, it would be an n by 1 column vector. The derivative there is also an n-dimensional vector. Everything is n-dimensional. The matrix itself is n by n. What is the unique solution of this system? I call this the beautiful generalization because I do think it is a beautiful generalization of something. It's that the unique solution of this generic initial value problem in n dimensions based on an unspecified matrix A can be written y equals a function of t equals something else. I give this function of t a special name. I use a Greek letter phi, or if you prefer, phi. In vector form, to emphasize it's a vector, I use a capital Phi, which looks like something from Mario Brothers, something Mario would jump off of. It's a function of t, but I also specified the initial condition as a subscript. This is just a function name. That's all it is. Capital Phi sub y0. It's just a function name. Y0 is just specifying what the initial condition is. We'll look back at the example in a minute, and when we have a special matrix A and a two-dimensional generic initial condition. But the beautiful generalization is that this unique solution is e to the a times t power, notice that's a capital A, times y0. This e to the at is called the matrix exponential. If you want to be a little bit more specific, of a times t. A is this n by n matrix. T is a scalar. T is a number. A times t could also be written as t times a, is just the scalar t times the matrix A, which means take every component of A and multiply it by t. That's what it means. And this is an n by n matrix when A is an n by n matrix. And I'm multiplying it times the initial condition.
Question. So this, you're multiplying A by every other t, but you're taking this thing, like each component to the power of e.
Well, not quite. So the question is, I'm in this matrix A times t. It's the same as t times a. I told you just a minute ago, this means take every entry of A and multiply it by the scalar t. But then I have this e there, and this is a power of e. And what was hypothesized, is a natural thing to hypothesize, is that must mean take every entry of A times t and make it the power of e to make a new matrix. That's a good guess, but it's actually incorrect. Okay? That would be, it turns out, a little too simplistic. How this matrix exponential is defined is actually with an infinite series. What? It's actually defined via an infinite series. E to the at is I, where that's the n by n identity matrix, that has all ones in the main diagonal from upper left to lower right, and zeros everywhere else. That's what I is. We've seen that in the 2x2 case. 1, 0, 1, 0, 0, 1. Plus A times t plus 1 over 2 factorial times A times t quantity squared plus 1 over 3 factorial times A times t quantity cubed, etc. forever and ever. This should look kind of familiar. In Calc 2, you should have learned that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial forever. And you learn about power series and Taylor series. That should be something you might have a couple brain cells remembering when you see it again. It's super important. That's a super important equation. And all this is a generalization of this, except x is the matrix A times t. But that begs a question. Can you really do that? Can I really make an infinite series of matrices and their powers like that? The answer is yes, though you have to prove you can. We're not going to prove you can. We're just going to trust that you can. That's really what e to the AT is. And it does not typically equal a times t with every entry being the exponent of an e. Unfortunately. However, we're still going to be able to figure it out. Right now, we're going to figure it out with technology, but in coming weeks, we'll figure it out how to do it by hand. It's all related to change of coordinates, skew coordinates. It's all related. Eigenvalues, eigenvector, all that stuff is related to this. Why is this the beautiful generalization? Why do I call it that? That's my name, by the way. Nobody else I know calls it that. I call it the beautiful generalization because I just think it is so beautiful. It's a generalization of the situation where everything's a scalar. You know, the differential equation in the very first lecture, dy dt equals a times y. Y of 0 equals y naught. Solution is y equals y naught e to the at. This is the exact same kind of thing, except with vectors. And if y naught is a column vector, you got to put it on the right, not on the left. It's a generalization of this fact right there. And it's beautiful that it works. So I call it the beautiful generalization. But again, it begs a question. How do you actually compute it? By the way, I think as far as flows go, I'll just say this can be related to something called the flow. I won't go into more detail today. I'll skip the flow today so we can do a linear algebra example too. So according to what we just did, I should be able to get the same exact answer that I got with d-solve value if I use that matrix exponential, which in Mathematica can be found with matrix exp. Mathematica knows A is a matrix. I think I can put a star t there to do times t. I could also put the t in front. I do want to multiply this by my arbitrary initial condition vector as well. If when I enter this, I get the exact same thing as you see here, I will have confirmed the beautiful generalization for this example. Cross your fingers. Okay, let's expand it. Maybe not. Is it the same? I think it is the same. Just written differently. Yeah, the first two terms there do correspond to this term here. Yep. These two correspond to this one. This one corresponds to these two. Yep, it's matching. It worked. Okay. So there's Mathematica's confirmation of this thing I call the beautiful generalization. But if you're going to understand the lectures, and you should work at understanding them, remember it's harder and important. It's fundamental stuff. If you've been neglecting the lectures, get back into it. This is meant to help you understand it all better. Examples help you understand theory, right? Theory sometimes kind of seems like it comes out of nowhere. It can be reasoned about abstractly. You can come to these kind of conclusions purely abstractly if you want. And that's good. But 99.99% of all people need concrete examples too, to help you understand the theory better. And then the theory ties the examples together.